Hey everyone, so for this lecture, we will discuss two topics under nuclear physics. So the first one is on nuclear mass, followed by the discussion about binding energies. These two topics are important later in our discussion of radioactivity. We have discussed before that any nucleus are made up of your nucleons, mainly your protons and neutrons. And we have the following mass for both proton and neutron. The total number of nucleons is described by your atomic mass number A. So this is the total number of nucleons, while the total number of protons refers to your atomic number Z. Thus, if you want to find the total number of neutrons, what you can do is to use this formula. The total number of neutrons N is equal to A, your atomic mass number, minus the Z. The atomic masses are measured with reference to carbon-12 atom, and we have this unit here, your atomic mass unit with this symbol U. By definition, so the mass of the carbon-12 nucleus is exactly 12 U or 12 atomic mass unit, and this is equal to 1.66 times 10 to the negative 27 kilogram as shown here. The mass of an isolated proton has been measured of about 1.0073 AMU, and that of a neutron we have 1.0087 U. Now, this table here describes the mass of our basic particles such as your proton, your neutron, electron, and positron. So in terms of kilogram, then AMU, atomic mass unit, and in terms of mega electron volt per c squared. Note that 1 AMU, 1 atomic mass unit, is equal to 931.5 mega electron volts as shown in our previous slide. You may think that the mass of a nuclei is simply the sum of its nucleon components, but in reality that's not the case. The total mass of a stable nucleus is always less than the sum of its masses of its separate pieces, the protons and neutrons. So, where has the mass gone? Therefore, we can write the following. The mass of your stable nucleus is less than the total mass of your protons plus the total mass of your neutrons. This difference between the total mass of separate nucleons and the mass of the final nucleus is then the total binding energy of that nucleus. So we have this thing or quantity called your mass defect or mass deficit, which is related to your binding energy. Now let's go to mass defect, also called the mass deficit. This is mainly the difference between the mass of an object, let's say this object, and the sum of its constituent particles. The mass deficit delta M must always be negative. So I'll write this negative so that the nucleus is in bound state or stable state. We can write the following that defines your mass defect. So this delta M AZ is equal to the mass of your nucleus minus the total mass of your protons minus the total mass of your neutrons. And this should be always less than 0. Therefore, stable bound states have negative binding energy. We can also express your binding energy or mass defect in terms of your delta M over 8. or this is the binding energy per nucleon, Az. So this is equal to this one, to the mass of your nucleus per A minus Z over A times the mass of your proton minus 1 minus Z over A times the mass of your neutrons. And this should be much less than the mass of your proton per neutron. Now let's go to the formal definition of binding energy. This binding energy is actually the energy you would need to split the nucleus into individual protons or neutrons. So if you have this nucleus with some neutrons and protons here, and you want to separate this into pieces, into its individual components, then you need this energy, the binding energy. As an example, let's take deuterium, which is stable against breaking up into proton and neutron. So we can write the following. So the mass of the deuterium minus the mass of its proton minus the mass of its neutrons. And we can write it as follows. This is equal to 1876.12 mega electron volt for deuterium in terms of energy, minus 938.27 MeV, which is the mass of the protons in terms of MeV, minus 939.57 mega electron volts for your neutrons, and this would be equal to negative 1.72 mega electron volts. Now let's try to calculate the mass defect or the binding energy of carbon-12. Let's start with this one. So your mass defect for this one is equal to 6 times 1.008664 U. This refers to your the mass of your neutrons, plus 6 times 1.007276 U. This refers to the mass of your protons, plus 6 times 0.000548858 U. This refers to the mass of your electrons, minus 12.000 U, which refers to the mass of your carbon-12. Note that we have defined your atomic mass unit in terms of carbon-12. So thus, we can calculate a value for a mass defect of about 0.098931 AMU. Now, we can convert this delta M, your mass defect, into its corresponding energy. So by multiplying it to 931.5 MeV per U, and we can get the binding energy, which is equal to 92.15 mega electron volt. So for this case, we have this value of binding energy. Okay, so now let's check this graph. So we have here for the y-axis, this refers to the average binding energy per nucleon in terms of mega electron volts. Then we have the number of nucleons in the nucleus. Let's start first at the leftmost side of this graph. So for A less than 20, what we can observe in this part of the graph is there's some form of oscillation here, or some variation in our average binding energy per nucleon as it rises by increasing the A. And between 20 up to 60, your average binding energy per nucleon starts to saturate until it reaches your A is equal to 60. This one refers to your iron group, which formed by nickel, iron, and cobalt, with about 9 mega electron volt per nucleon of binding energy. And this is the peak of this graph, this 9 mega electron volt per nucleon. And for A larger than 60, this part of the graph, what we can observe is the binding energy per nucleon decreases slowly, wherein the general mean is about 8 mega electron volt per nucleon.